we have already seen two combinations, that is series and parallel, right? So in series, R equivalent is equals to, suppose if there are three, it will be R1 plus R2 plus R3. And in parallel, R equivalent will be, actually 1 by R equivalent will be equals to 1 by R1 plus 1 by R2 plus 1 by R3. So in simple circuits, we can directly proceed by using this, but in sometimes your circuits will be a little complicated, and in such cases we have few methods which we will be using or which will be applying to solve such circuits, or in order to find the equivalent resistance. So the next method is method of equipotential points. Method of equipotential points. So let's revise quickly what we have understood till now. Suppose there is this circuit, and in this circuit there are different resistors and cells. So suppose this is one of the resistor R1, this is another resistor R2, and there is a cell here of some EMF E. Right now, what happens is when the current starts flowing through it, current will flow from positive to negative direction. So here there will be a drop, and that drop will be I into R1. You can see here there is no division of current, so the same current will flow everywhere. And here that division will be, that drop will be IR2. Drop in what? Drop in potential. So if I say here we start from 5 volts and here there is a drop of 2 volts, then here there will be drop of 3 volts. So the 5 volt with which we started, drop of 2 volts here and drop of 3 volts there. So that's how this is calculated, right? This thing here will be called V1, that is drop across R1. This drop will be called V2, that is drop across R2. And we say that E is equals to V1 plus V2. Right? So that's how the drop happens. Now that means what? Suppose here we say that the potential is 5 volts, then here it will be 5 volts. Then there is loss of 2 volts. So here it will be 3 volts. 5 minus 2, 3. And again there will be loss of 3 volts. So here it will be 0 volt. That means here also it is 0 volt. So the points where the voltage or the potential is same, that is called equipotential points. So equipotential point, from the name itself, it should be clear. These are the points having same potential. So for example, here in this figure, suppose I say this point is A, this is B, C, D, then, and suppose this is E. So A and B have same potential. That is, so if there is no resistor in between 2 points, that means there won't be any potential drop. So the points will be called equipotential points. So this A and B is equipotential, and same way D and E are also equipotential, but potential of C is different. So this is 5 volts, this is 0 volts, and this C, which is alone, that is 3 volts. That is the potential of that point, or potential at that point. Right now, when we have studied earlier, we said if there is a conductor, any wire, every wire or each and every wire or any wire will always, if there is a current in a wire, that wire will always offer resistance or opposition to the flow of current. It will be always. But when we say that there is no drop here, that means we are saying that the drop here is negligible as compared to the drop which we'll see across R1. Right? So there is no zero resistance. There is nothing like zero resistance. What does it mean when we say there is zero resistance? We just want to say that the resistance of that section is negligible as compared to other elements or sections in the circuit. Right? So now let's come back to this process or method, which is method of equipotential point. So this method is based on identifying the points of same potential and then we join them. So what we have to do here is identify the points having the same potential and then we join them. The basic rule to identify the points of same potential is the symmetry of network. So equipotential points. How are we going to identify that? So we are going to observe if there is any symmetry in the circuit, right? And this method is important because if you are going to solve this and find equivalent resistance without these methods, it will take a lot of time, right? So what we do in the circuit, we find or we try to find symmetry if there is any symmetry. Right? Now in any access or in any network, this circuit sometimes is also called it can be like any, even this can be your one of the circuit diagrams. So this is also called network or circuit, both are same. So in a given network, there may be two axes of symmetry. So we have to find two axes of symmetry. There may be two, there may be just one. So two axes of symmetry. And what are they? They are parallel axis, parallel axis of symmetry. What exactly is parallel axis of symmetry? The axis which is along the direction of current flow, along the direction of current flow. So that will be called parallel axis of symmetry. And you must have guessed now that the second one will be perpendicular axis of symmetry, right? So that is what? That is perpendicular to the direction of flow of current. So that is perpendicular to the direction of current flow. So these are the two axes, right? So how to identify? Let's see an example. How to identify these two axes of symmetry. So suppose we have a network like this. Okay, and there is a straight line like this. and another right. Now the current flows, suppose this is the entry of current from the network and this is the exit of current from the network. Let this point be A and this point be A dash. Okay, now in these you have some resistors. In all these sections you have some resistors in all the sections. Right, now in this AA dash, if there is an imaginary line, right, imaginary axis which is joining the point A and A dash, if I'm able to join this by an imaginary line. So this imaginary axis which you see here, first the circuit is symmetric and it cannot be symmetric just like that. For this the resistors have to be equal. I mean they have to be symmetrically equal. So this AA dash which we see here by this dotted blue line, this is our parallel axis of symmetry because this is the direction in which the current is also flowing. So AA dash is parallel axis of symmetry. And if this point is say B and this point is B dash, and if we are going to join this as well, then this line B dash will be called or will be the perpendicular axis of symmetry. Not all perpendicular axis and not all parallel axis will be axis of symmetry. This will be axis of symmetry only if the resistors values are symmetric. That means suppose if all the resistor values are R, then I can say that it is symmetric. But if these resistors have different values, that is non-symmetric, then it won't be a axis of symmetry. Right? So this axis of symmetry is not mandatory. It's not always present. Axis of symmetry will be there only if network has a symmetry. Right? So that is the first part which we have to do, is to identify the parallel axis of symmetry or perpendicular axis of symmetry. Right. Now second is the points lying on the perpendicular will or may have the same potential. Right? So that is the second point, and we'll explain it why. Points lying on the perpendicular axis may have same potential. Right? Perpendicular axis of symmetry. It's simple because both these two, current comes here and it gets divided into two paths, and two paths are symmetric. Symmetric in the sense they have same resistors, they have same path, so we say that it is symmetric. So that means the current will also get divided equally. So if there is suppose 10 ampere current here, so it will be divided into 5 ampere and 5 ampere. And so that's why, what is potential drop? Potential drop is IR. So that means the potential drop as you move ahead, that is here, here, these if you move this much, you reach here, the potential drop in this section and the potential drop in this section will be same. So now move to the next axis, that is next point, that is here and here. So here and here again you will have the same potential, that is at this let us give some name to these points. Let's say this point is 1, this point is 2, this is 3, this is 4, and let this be 0. So what all points are having same potential? We can say that, for example, in the above figure, the point 2, 0 and 4 are equipotential. I hope this is clear. So these are the points which are equipotential, right? So from 1 to 2 or from 1 to 4, if you imagine or if you consider this path, 1 to 2 and then 1 to 4, both the paths are symmetrical, identical. So that's why the energy lost or the potential lost in covering these two paths must have been same. So that's why we say that point 2 and point 4, this point 4 and this point 2, they are in same potential. And same thing is about this point O. So if you see here, the path here is little different, but because it is on the perpendicular axis, we say that this will also have the same potential. So that was our second step or second step of this method, that is of equipotential points method. Now let's move to the third step. In the third step, the points lying, we are talking about the points lying on the parallel axis. Now, because parallel axis means which we believe or which we assume that will have the same current. So if it is having same current and if there is a path length, so that must have some resistance, and because there is a resistance and there is a current, so you reach here or here or here. Potential here, here and here are not going to be same. So V1 is not equal to V2, is not equal to V3. There must be some potential drop. So for example, if we start from 10 volts here and here if there is 0 volts, that means obviously all of this cannot be at same potential. This is not possible. So that is our second, or that is our third step or third point, that is points lying on the parallel axis. Points lying on the parallel axis of symmetry can never have same potential, and whatever we have drawn below, this is the explanation for that, right? So now if 2 points are having same potential, that means the current won't flow through or between those 2 points. The network can be folded about the parallel axis of symmetry, and the overlapping nodes have the same potential, right? So that is the next step, that is once you have this parallel axis of symmetry, we can actually fold it along this parallel axis. That is, here suppose it is written on a paper and I can fold it. So if I fold it, what will happen? The 1, 0 and 3 will remain as it is, but 4 and 2 will overlap, right? And suppose we have some more points, say 1, 2, 3, 4 we have given, say 5, 6, this is 7 and 8. So this figure, right, if I fold it along this AA, so what we are talking about is that the network can be folded about, fold the network about the parallel axis. So fold it. So because it is parallel axis of symmetry, so that means because it is axis of symmetry, if you fold it, it will cover it. The both the parts will cover each other, right? And few points will overlap the nodes of the other section. So there will be, due to this, there will be overlapping of nodes. What are nodes? Nodes are nothing but junctions or points of intersection, right? For example, here in this case, it is uh, 6 and 5. 6 is point of intersections and 5 is point of intersections. And if I fold it along A dash, 5 and 6 will overlap, right? Then what else will overlap? 2 and 4 will overlap, and 7 and 8 will overlap, right? So let's okay, or simply I can write here, assuming that you have understood what is there in the figure. I can say now clearly the points which are overlapping. So overlapping points are now, so what are the points that are overlapping? It is first, it is the 5 and 6, second 2 and 4, and C is third, it was 7 and 8 are overlapping. Now we have already told that 2 and 4 are equipotential. Why? Because not just 2 and 4, 2, 0 and 4 are equipotential. Why? Because they lie on the parallel, on the perpendicular axis. So, and the overlapping nodes, there will be overlapping of nodes, and these overlapping nodes have same potential. So they must have same potential. So that means A, it is 5 and 6, B will come to B later, C 7 and 8. That means V5 is equals to V6. Potential at 5 is equals to potential at 6. Potential at 7 is equals to potential at 8. And the last, that is 2 and 4. It is not just 2 and 4. 2 and 4 were overlapping. And there is also a point 0. So 2, 0 and 4. So we'll say V at 2 is equals to V at 0 is equals to V at 4. So now these are the set of equipotential points. Not all of them are equal. It is like this. 3 different sections. V5 is equals to V6 and V2 is equals to V0 is equals to V4, and V7 is equals to V8. Right? So that's what we get from this finding the after finding the parallel axis of symmetry and perpendicular axis of symmetry, we get this data that V5, V6 is having same potential, V2, V0, V4 are same potential, and V7, V8 are same potential. Right? So now the network which we have seen, that can be split up into two equal parts about the parallel axis of symmetry. What will be that? Let us see that. So we have to understand one point here, that is no current flows between points of equal or same potential, obviously if they are connected, provided they are connected. Right? So let us take this part and okay, anyways, if I now we have to, and using this we have to now simplify the circuit. So what we are going to do now, we had this the image which is there above, right? So keep that in mind, and keeping that in mind, what I can think of is drawing something like this. This is our imaginary axis, that is A A dash, right? Sorry. There was a resistor going from here to here, and then here there were two resistors which was coming to this point, and another was going in the same direction. I hope you remember, right? This is your point 2, this is 0. Okay, so this was having resistor R, right? And all resistance are actually R, so I'll just write it like that. Okay, next, in the next segment, we had like this, and this was going to this point. So it was like this. This is after folding it along AA dash. I hope this is clear. So this point, I think we started with 1. So this point is 1. This point is 0. This point is 1. This is 0. This is, sorry, this is 3. Here, the 2 and 4 overlapped, right? And this point was where I think 5 and 6 overlap, and this is where 5, 6, I think this is where 7 and 8 overlap. So now if you see this R, this is showing, this is because it is in 2D, we have folded it. So the resistors have overlapped. So it won't show you all the resistors because you are seeing only the one side of this. On the other side, there is one more R. That means this here, there is one more R. And that R is connected from 1 to 6. This R which we see here, that is connected between 1 and 5. Same way there is another R which is connected between 1 and 6. So let me draw that as well, and let me draw it using some other colors so that you remember that this is actually in the background. So between 1 and this 6, there is another resistor in the back. Between 6 and 2, there is another resistor. Between 6 and this, again there is a resistor here. Right? And same thing for this section. So these are the total resistors. The one in the light green, they are, suppose they are in the background. But now we can clearly see that between 1, 5 and between 1, 6, as we said, 5 and 6 are equipotential. And remember the definition of parallel connection. When the potential difference across two resistors which are connected together is same, right, and they are not connected sequentially, that is one after another, but their one end is connected together, another end is also connected together, and they have the same potential difference, then we say that that is a parallel connection. So that means now these two, between 1 and 5, there are two resistors, that is R and R, and they are in parallel. Then between 6 and 2 comma 4, that is this point, again there are two resistors. So now this I will, instead of writing two different, what we have written is two different this thing resistors. So instead of doing that, let us have only one equivalent resistor. That is, now you try to simplify this. So another level of simplification will be what? That it is like this. So this between 0.1 and 5 or 6, the resistor is R by 2, right? Then again between 5, 6 and 2 comma 4, this is the point 2 comma 4. There the resistance is again R by 2, because 1 by R and 1 by R will give you R by 2. Equivalent resistance will be R by 2. Next it will be here, and again this is R by 2. Again next level it is R by 2. Clear? Now from here you have a point here, and from here you have a point here, and this section is also R by 2, and this section is also R by 2. As you can see here, these points are not connected. So now I think this is very simple now. So what do we have now? Again, if you want to simplify this, what will we get? We'll get R by 2. Then in this section, there is, I mean this section, that is this R by 2 and R by 2, they are in series. So this together will be R, and this will also be R. So this, if I am trying to write it, or the simplified version of this, so what will be that? It will be R by 2, the first R by 2, then there is this and this section. This is R, this is R, right? What are these two sections? This is actually this section, right? And next will be what? This will be R by 2. So now again R and R. So equivalent of this, that is in parallel. So this will be R by 2 again. So now the simplified form of this will be R by 2, R by 2 and R by 2 in series. So total, that is R equivalent, will be equals to 3R by 2. So this is the method of solving some complex but symmetrical circuits. You have to identify parallel axis, you have to identify perpendicular axis, you have to fold it along the parallel axis, then you find the points of the points having equal potential, and then you the points, the resistors connecting points of equal connected between equipotential points, they will be the resistors in parallel, and then you simplify that, and after simplification you keep on doing that, and you will end up having your final value. That is what we can see here, that is 3R by 2 in this particular case. Right? So that's how we are going to solve such problems. Now, the one which you have seen here, you have got R by 2, right? So each part has resistance R dash, then the equivalent resistance, as we have already seen, that is R dash by 2. So this is how we are going to solve such circuits. Now, based on this, again, I'll send you some more problems to solve. And I think the session will now stop because just 1 minute is left. And I think